Hello, I'm the motivating Mr. Daycock, and today I'm going to give you a more formal sense of differentiation. So let's consider what we were doing last time. We had some function that gave us at a certain time 0, 1, 2, 3, 4 would give us a position, which was, for example, x. In this case was 0, 1, 4, 9, 16. And we could see that x was equal to t squared. And then we looked at small values, small changes. So our change in x over the change in time, and I'm using change as a little triangle here, gave us our velocity, or at least an approximation of our velocity, or the average velocity between the points that we picked. And it turned out in this case that the velocity appeared to be 0 to, not 6 there, 4, 6, and 8. And it appeared that our velocity was equal to 2t. But let's consider it more formally. We couldn't justify that. We couldn't prove it. We just said it was looking like it should be 2t. So let's see if we can prove it this time. Let's see if we can justify it. And we're going to do that by thinking about what it was we were doing. So we were taking t, and we're taking it, say, if we wanted to find out the point 3, we're taking 3, and then maybe a little bit further along, 3.1. And then we're working out the x values, which was 9, 3 squared, and 3.1 squared was 9.61. And then we were going, well, my velocity should be my change in x, so 9.61 subtract 9, the change in x, divided by the change in time, which was 3.1 minus 3. And that should come out as our velocity, or at least our average velocity over that time period. And so that gave us 0.61 divided by 0.1, which was approximately 0.6, not exactly 0.6, but almost 0.6. And then we went, well, what happens if we went even closer? We went from 3 to 3.01 or 3 to 3.001 and so on and so forth. What happens as we get closer? And it appeared to get closer and closer to 0.6, which seemed to justify the idea. But what we want to do is get it in a general sense. We want to get it in a sense that means that we're sure. We can't question it. There's no question of whether or not it's 0.6. And the way we're going to do that is we're going to do exactly the same table, exactly the same idea, except I'm going to go from 3 and then I'm going to use algebra. I'm going to go, my next point is 3 and a bit. I'm going to use h here to indicate the and a bit, because it's just a variable. So we're starting at 3 and we're going to 3 and something else. And therefore, what is x going to be? Well, we know that x is equal to t squared. So here the x is going to be 3 squared, which is 9. And here the x is going to be 3 plus h squared, which is going to be, let's expand it out properly. Make sure it's clear. 3 plus h, well, in fact, let's take a moment and go remember that 3 plus h squared is equal to 3 plus h multiplied by 3 plus h. And we're going to end up with 3 times 3 is 9, 3 times h is 3h, 3 times h is 3h, and then times 8 is h squared. So we can answer this as 9 plus 6 lots of h plus h squared. And now we still want to do the change in x divided by the change in t. So the average velocity between this point 3 and the point 3 and a bit, so again 3 and 3 and a bit, is going to be, well, it's the change in x is our 9 plus 6h plus h squared minus 9 all over our change in t is 3 plus h minus 3. And now hopefully, if you're reasonably good at algebra, you can see what's going to happen here. 9 take away 9, well, that is 0. So on top we're left with just 6h plus h squared. And 3 take away 3, that's also 0. And so on the denominator we're just left with h. And that's really nice. And now, in fact, I can factor this top. I get factor out the h, and I get 6 plus h multiplied by h, all divided by h. And those h's will divide through if I divide top and bottom by h. And I'm left with my velocity, the average velocity over this time period, the average velocity between 3 and 3 and a bit turns out to be 6 plus h. Well, now what can we do? Right? What we want is we want h to be as small as possible. We want that and a bit to be almost nothing. So what we can say is, well, what happens as our h goes to nothing? Well, our velocity will then tend to 6. Exactly. And that's what we wanted. We said up here that at time 3, our velocity should be 6. And so what we're doing here is we sort of get a sense that, although it doesn't really make any sense for our jump, our little change, to be nothing, as it heads towards nothing, we can formally say that it's definitely looking like it's heading towards 6 because of this. If this here was 0, then this would definitely be 6. So as this tends to 0, this v tends to 6. And this is the formal concept of limits. And so what we want to do, what our idea is here, very formally, our velocity is equal to the limit as our h tends to 0 of the change in x over the change in t. But imagine our x is just some function of t, so our x is equal to f of t. Well, then the change, we're going from t to t plus h. Well, that means that our x goes from f of t plus, well, f of t to f of t plus h. And we're left with the velocity being equal to the limit as h tends to 0 of, well, the change in x is f of t plus h minus f of t all over t plus h minus t. And then, of course, these t's cancel just as before, and we're left with our velocity is equal to the limit as h tends to 0 of f of t plus h minus f of t all over h. And this is the formal definition of a derivative. V is equal to the limit as h tends to 0 of f of t plus h minus f of t all over h. Except we want to think of v as related to x, really. So what we do is, rather than calling it v, we call it the change. Our v is equal to the change in x over the change in t. But we want to think of that change as being absolutely tiny. So rather than writing this triangle delta, we write it as v equals dx by dt. And so we're going to write this here as dx by dt is equal to this. Okay, now with this in mind, we can actually go a little bit further and prove that if x is equal to t squared, then v is equal to 2t. Not just for one point, but at every point. This is a little bit harder now, but it's still exactly the same principle. We've got t and we've got x. Well, in this case, we're going to actually say, well, we want t to be some variable. We want it to be t. So we're going to go from t to t plus h, so a little bit more. And the x value, well, it's going to be t squared and t plus h squared, because we want to square those t values. And then we can expand out this one, we get t squared plus 2 lots of th plus h squared. And now plugging that into our formula, we're going to look at our dx by dt, i.e. our velocity. It's going to be equal to the limit as h tends to 0 of, well, the change in x is t squared plus 2th plus h squared, because that's our end t. And we're going to subtract just t squared. And then we're dividing that all by the change in t, which is our end t is t plus h, and we're going to subtract t. So exactly the same before, there's some lovely cancelling here. That t squared cancels with this minus t squared, that t cancels with that, and we're left with the limit as h tends to 0 of 2th plus h squared all over h, which is equal to the limit as h tends to 0 of, factoring out this h, we can do some cancelling here, and we're left with 2t plus h, and then as h tends to 0, that's equal to just 2t. And so our velocity is 2t, regardless of what's going on. And if we were to carry this on, we could actually see that if x was equal to t cubed, then it would turn out to be that v was equal to 3t squared. And similarly, if x was equal to t to the 4, then it would turn out that v was equal to 4t cubed. And this here is called our power rule. And though you may be able to spot the pattern at this point, what happens is if we have x equals t to the power of n, then our velocity, or let's call it dx by dt, is equal to, we have to multiply by the power, so n, and then we subtract 1 from it, nt to the n minus 1. And that is our power rule for differentiation, using velocity from the first basic principles. Okay, thank you very much for watching, and I'll see you in the next video where we will be using this power rule. Thank you very much.